much yet, but we need to review these ideas so that it makes sense, because the next section is proving continuity. So then we will have to use some calculus notation to prove that something is continuous at a point. But we need to kind of know what these ideas are first. So you have two types of discontinuities that we are going to focus on. Removable discontinuities and non-removable discontinuities. And removable discontinuities are holes in the graph. So I have left a space here to draw ourselves an example of what that looks like to remind ourselves about holes in a graph. And a hole in a graph, just, the function could look like whatever. You just have a single point that is not defined. Okay, so this point right here is our removable discontinuity. They call it a removable discontinuity because you could remove it with a single point, right? All you would have to do is put a single point right here, and now your function is continuous at that point. Yes. You can, yes. There can be multiple holes on a graph. So holes are one type of discontinuity. They are probably going to call them removable discontinuities in like a multiple choice official AP situation. I call them holes most of the time, but know that those two things can be used interchangeably there. Non-removable discontinuities, there's a couple different things that can happen for non-removable discontinuities. Non-removable discontinuities can be jumps or vertical asymptotes. So a jump, if we draw ourselves an example, looks something like this, where we would have a graph that does maybe something like this, and then you got an open circle, and then it could be a open or closed, I guess, but you jump down to like another part of the graph. These are typically on piecewise functions. So typically piecewise functions are where we're going to see this. There are a few types of other functions, but we don't really have to do this. Sorry, Hunter is needing. I got the controls still on his phone, and he needs to download something for engineering. All right, so vertical asymptotes, they can look several different ways, but the main key factor there is that you have some sort of vertical line that you get closer and closer and closer to. It could look a lot of different ways. It could be one-sided. It could be from both sides. They could both go to infinity. They could both go to negative infinity. It really doesn't matter. Any type of vertical asymptote is going to cause a non-removable discontinuity in your graph. These non-removable discontinuities are non-removable because it would take a lot more than a single point to fix it, right? You'd have to move the graphs together. Vertical asymptote, there's not much you can do with that, so they're non-removable discontinuities. There. These are a lot of times referred to as vertical asymptotes or jumps in the graph on multiple choice questions if they're asking about them for those. So, things that can cause discontinuities. All right. So I've made us a list of things we need to be on the lookout for. Negatives under a square root or any even root cause a discontinuity. Odd roots are okay. We can have negatives under a cube root. But square roots are what you're going to see most often. If you had a fourth or a sixth or eighth root, you also cannot have negatives underneath those. So if you have negatives under a square root, that is going to cause a discontinuity. Zeros in the denominator of a fraction cause discontinuities. Those we looked at quite a bit in pre-cal, and we're going to see more today. A number less than or equal to 0 inside of a logarithmic function. So we can't put 0 or negatives into log functions. Those cause discontinuities. Logs have a natural vertical asymptote, right? So any log function you're looking at is going to have a vertical asymptote. Piecewise functions that, or a piecewise function that has a hole or a jump in the graph. You could have either one of those. Jumps are most typical, where your two pieces of your graph do not meet up. And then some trig functions have vertical asymptotes. For example, tangent. Really, all of them except for sine and cosine have vertical asymptotes there. They're not as common to see, but you do see them some. Okay. So let's remind ourselves particularly about these rational functions and when we're talking about zeros in the denominator. So when we're looking at zeros in the denominator, we want to factor top and bottom, but bottom's the only part that gives us the discontinuities. So like for example here, for this function, I need to factor this. What should I do first to factor it? Taking out a 2 is going to make it the easiest. Technically, you can factor it without taking out that 2, but then sometimes you don't see something that will cancel if you do that. So once we take out the 2, then we can factor this. And so we would have x and plus 3 minus 2, I believe is how that one will factor. So let me write it over here. We got x plus 3 over 2 times x plus 3 x minus 2 right here. And I'm going to put some parentheses there too. So your discontinuities come from the denominator, right? So you've got x equals negative 3 and x equals positive 2 are both going to be discontinuities for that. Because if I plug in negative 3 right here, it's going to give me 0 for that piece. If I plug in positive 2 right here, it's going to give me 0 for that piece, making the whole thing 0 on the bottom. So negative 3 and 2 are both discontinuities. I need to know what type of discontinuity here. So x plus 3 will cancel top and bottom. So the one that cancels, what do we get at that point? It's a hole in the graph. So at negative 3, I have a hole, or I'm going to call it a removable discontinuity, since that's what my directions are telling me to do. And then for 2, it does not cancel, so that is going to be a non-removable. Specifically, it is a vertical asymptote, if you want to be more specific about that. So the zeros in the denominator that do not cancel are vertical asymptotes. The ones that do cancel are holes. So if we look real quick at the second one here, that top will factor into x plus 2, x plus 3. And on the bottom, that'll factor into x plus 1, x plus 3. It is important to remember for this, your discontinuities only come from the denominator. It's okay to have a 0 in the top. So it's x equals negative 1 and x equals negative 3 there. And which one of those is going to be a hole? The x plus 3, because it cancels, so that means our negative 3 right here, that is our removable discontinuity, and x equals negative 1 is our non-removable. You also have this x plus 2 that's just left here on the top. What is that? It's an x-intercept, or a 0 of the function. But it tells you where the y value is 0 for that. It is not a discontinuity, so you just ignore it for these types of questions right here. The only reason you even have to factor the top is to see which ones will cancel, right? If they only asked for discontinuities and didn't care, If it's a whole or a vertical asymptote, you wouldn't even have to factor the top. You guys remember doing this from pre-cal? Coming back, hopefully. All right, now let's look at a couple that you would probably didn't have. We might have done 4 in pre-cal. I know we didn't do 3. 3, we definitely have a discontinuity at x equals -1. Because if I plug in -1, I get a 0 in the denominator of that function. So I've got some type of discontinuity there. But does x plus 1 cancel with absolute value of x plus 1 in the top? Like, not really, but almost, right? Like, kind of, almost cancels. All right, so let's think about what this graph is going to look like. Let's try to picture it before we actually, like, graph it, right? We'll type it in Desmos here in a minute. So let's think about, like, plugging in some numbers, right? Clearly, -1 is the most interesting point on this graph. So let's start with some of the, like, approaching -1. So let's start with, like, -3. So if I do absolute value of -3 plus 1 over -3 plus 1, in the top, I get absolute value of -2. In the bottom, I get -2. That gives me +2 over -2, which gives me -1. So I get -1 for that. Okay. If I plug in -2, then I've got absolute value of -2 plus 1 over -2 plus 1. And that gives me absolute value of -1 over -1. And that is also -1. And I can't plug in -1 because that gives me 0 over 0. What about if I tried, like, -1.5, right? I've got absolute value of -1.5 plus 1 over -1.5 plus 1, which gives me absolute value of -0.5 over -0.5. What do I get for that? Still -1, because I'm getting positive 0.5 over -0.5, which is giving me -1. So what does it look like we're getting all the way up to -1? Like, if I have -1.0001, what do you guys think I will get? Still -1, right? So definitely from the left side, it appears that we are approaching -1 if we do a limit there. Let's think about from the right side, okay? So if I'm picking numbers bigger than -1, so if I pick, like, +1, now I'll be doing absolute value of 1 plus 1 over 1 plus 1, and that will give me absolute value of 2 over 2. What am I going to get there? 1. Okay? If I try 0, I'm going to have 0 plus 1, 0 plus 1. I'll get 1 over 1. What do I get again? 1. If I try, like, -0.5, I've got absolute value of -0.5 plus 1 over -0.5 plus 1. I get absolute value of 0.5 over 0.5. What am I getting again? 1, right? If I did, like, -0.999999999, what would I get? 1. So what's happening with this is I don't actually have a vertical asymptote on this. Normally, if I have something in the denominator that does not cancel with the top, I usually have a vertical asymptote. But this is a different scenario. This does cancel most of the time, right? And whenever we're getting positive numbers, these do cancel and you get 1. Whenever we have the numbers from the left side, it almost cancels out and we get -1, right? So if I were to graph this, if I put into Desmos y equals absolute value of x plus 1, oh wait, over x plus 1, it's just a horizontal line that jumps up to a different horizontal line at our point of discontinuity, right? So in this case, we have a jump in the graph. So if they're asking you for removable or non-removable, well, it's non-removable, but specifically it is a jump, not a vertical asymptote. So at x equals -1, we have a non-removable, which is a jump here and not a vertical asymptote. They put these on the AP exam fairly often. They're just like this. The equation will look just like that. It might be absolute value of x plus 2 over x plus 2, but it's very similar to this. They put them on there pretty often. So anytime you see these that almost cancel, they are going to give you a jump for this. Yes?
Like to answer this, would we just say no removal, or would they ask about if it's a jump or a vertical?
It'll usually be a multiple choice question whenever you see something like this, and there's usually an answer choice that says something about a jump in the graph for that. So they're usually more specific, because we could classify this as non-removable from the very beginning without doing any work, because it doesn't cancel with the denominator. But it's also not a vertical asymptote like we usually see for that. Okay, now I did a bunch of work here because I was wanting to explain and show you guys why, because of this. Whenever you see these in the future, you don't necessarily have to show all of that work where you're like figuring out. It's a strategy if you forgot it, if it's like familiar and you're like, oh, I can't remember what Ms. Hyatt said about that. Let me try a few things. But we should just catalog in our minds now that if we see absolute value of something over the same thing without absolute value bars, we're going to have a jump in the graph for that. Okay? All right, let's look at 4. 4 is a composition of functions. So it's wanting us to do f of g of x. We're taking g and we're plugging it in right here to our f function. So f of g of x is going to be 1 over x squared plus 3 plus 2. And we could simplify that a little bit by putting the 3 and the 2 together. So 1 over x squared plus 5. So in this, we have a rational function. We got a denominator. We need to make sure that denominator is not equal to 0. Usually we factor. Will x squared plus 5 factor? It will not. So in this case, we could try another strategy. What we know is that cannot be equal to 0, right? So if we're trying to find discontinuities, we're looking for where this equals 0. X squared plus 5, if I set that equal to 0, then that's going to give me the place where I have discontinuities. So to solve that, I would need to subtract 5 first. Oh, but what's going to happen here? Yeah, if I square root both sides, I'm getting I square root of 5 plus or minus I square root of 5. Can you find I square root of 5 on a graph? You cannot. That's not a real number. So when this happens, this should be an indication to you that in this case, there are no discontinuities. There's no real numbers that are going to make this 0. Think about what you're doing to your numbers. Think about plugging a number in here. You are squaring the number. So no matter what number you plug in, once you square it, what's going to happen to it? It's going to be positive, because when you square something, it's always positive. So if I take a positive number that I've got here and I add 5 to it, it's still positive. It's more positive than it was before, right? So that has to always be positive. It could never be zero unless you're considering imaginary numbers, which do not have any place on the graph, so it's not going to cause a discontinuity. So you would have no discontinuities here. And that happens pretty frequently, really. The more you do, the more you'll start to notice, oh, x squared plus 5, that's a positive plus a positive. That can't ever be 0. So you'll see those. All right, questions so far? All right, the one I'm not sure if we looked at it quite as much is piecewise functions. So when we're doing piecewise functions, we are graphing 3 different functions, and you're like cutting out this piece here, and this piece here, and this piece here, and you're sticking them all together, right? So they are only going to have discontinuities at the points where they sort of connect, right? Or if you have a function that has a discontinuity within these. So like, for example, if I had 1 over x somewhere that has a vertical asymptote at x equals 0. So I could have something there. Usually they don't give you that, but they could. So let's think about each piece of this piecewise function. X over 2, what type of function is that? Is it a line, parabola, absolute value, rational? What have we got there? It's just a line. Because it's really like 1/2 times x. The x is not in the denominator. Is that piece going to have any discontinuities in the piece? Lines are continuous everywhere, right? Just a regular line. What about absolute value? What do those look like? So absolute value of x minus 1 over x minus 1 would have a jump. But just absolute value of x minus 1 itself, that's just the V shape. Okay? It is continuous everywhere. So continuous. What about a square root function? You do have an issue with a square root function, and that is if it's giving you negatives underneath the square root. But if I'm only using this for 3 or bigger, am I going to get any negatives under a square root? I'm not. So all 3 of my pieces are fine. What I've got to worry about is where they connect, right? So I'm going to have you guys use limit notation for this, and that is because tomorrow when we do continuity, you really need to do limit notation for this. I know that you could do this much faster without writing the limit notation, but tomorrow we have to prove continuity. Those usually show up on free response questions where you have to show your work, and without limit notation, you're not going to get that stuff right. So my first issue is right here at -5. I need to see if my 2 pieces meet up at -5. And the only 2 pieces that are concerned with -5 are the top and the middle. So what I'm going to do is I'm going to do the limit as x approaches -5 from the left of f of x. And I'm also going to do the limit as x approaches -5 from the right of f of x. Now, just in preparation for tomorrow, we're using limit notation here. You could shortcut it, really, and that would be fine. So, and I'm going to even go a step further because from the left side, that's where x is less than -5, right? That's the top function. In general, piecewise functions are always arranged with left, middle, right. They go from left to right in the order that they give them to you. So the left function is x over 2. So what we're really doing for that piece, limit as x approaches -5 from the left of f of x, is the limit as x approaches 5 from the left of x over 2. Most of these are going to be direct substitution problems. So you're going to have -5 over 2, which is -5 over 2, -2.5 if you want to do a decimal. We want to do the same thing over here from the right. From the right, we'll be approaching -5 from the right of the absolute value of x minus 1, which means direct substitution again. Absolute value of 5 minus 1 there gives us absolute value of negative 6, which is 6. Okay? Is my function continuous there? It is not, because I've got a jump in the graph, right? From our left side, we're approaching negative 5.5 halves. From the right side, we're approaching positive 6. Those two do not meet up. So if you don't get the same number there, then you're going to have a discontinuity. So we have a non-removable specifically a jump at x equals negative 5. Okay. We also want to check at 3, because we got another part where we got two pieces of the graph that are coming together here. Now, let's just look at it real quick. So if I'm just trying to figure this out quickly, this is a multiple choice question. Nobody's asking me to show my work. Is this going to be continuous? It is, because if I plug in 3 here, I'm going to get 2. If I plug in 3 here, I get the square root of 4, which is 2. So they can be done much more quickly just by, like, most of these are going to be direct substitution, plugging them in. So when you get multiple choice questions for this, do that. In preparation for tomorrow, I'm going to show you everything that you should write. So you're going to have, like, limit as x approaches 3 from the left of f of x, which specifically would be the limit as x approaches 3 from the left of absolute value of x minus 1. Direct substitution problem, absolute value of 3 minus 1. That is going to give you 2. And then you would also do the limit as x approaches 3 from the right of f of x, which is the limit as x approaches 3 from the right of square root of x plus 1, which is going to be square root of 3 plus 1, which is the square root of 4, which also equals 2. So we have no discontinuity. At x equals 3. Technically, you don't really have to write that because they were asking for where there were discontinuities, but just to be clear. Also, do watch out. There is a chance that you get the same number, you get 2 on both sides, and you could still have a discontinuity. How could that be? Like, let's say I got 2 here and 2 here. What could I change about this function where it would still have a discontinuity? Good. If I don't have an or equal to with one of those numbers, that means I got an open hole and an open hole. They're at the same spot, but both of them are open, so you have a hole in the graph if that happens. But you've got an or equal to with one of these. If you got an or equal to at both points, it's probably a mistake because it's not a function if they do that. Right, it wouldn't pass. Well, yeah, because you would plug 3 into both of these, even though it's the same point, but it's just not going to be like that for those. Okay, so try the next one. Okay, I'm going to hide my screen while I do this one. you're getting 0/0 on that first one. So we're gonna have to solve that a certain way. Now on the second one, what do you get? On the 5x, what do you get? You just get 0. That one's very simple. It is just a direct substitution part. So here's what I've got so far. I didn't finish it because right here, if I plug in 0, cosine of 0 is 1. 1 minus 1/0 is going to give me 0/0, which is not a number, and I can't do it that way. Any ideas on what I could do? Let's see, will the conjugate work on that one? It's almost. The quickest way on this one is that special limit that we know and are supposed to memorize, but may or may not have memorized, is the limit x approaches 0 of 1 minus cosine x over x equals 0. So if we go over here and take out a negative right here and write it this way, the limit as x approaches 0 from the left of negative times 1 minus cosine x over x right here. Well then, this stuff right here, all of this stuff, that is just going to have a limit of 0. So we would get negative 1, because it's like a negative 1 right there, times 0, which does, in fact, just give us 0. And so this function does not have a, technically, like it does, cosine x minus 1 over x has a discontinuity at 0. Does that matter for the domain that we're given? It does not, because that means we got like open circle at the end of this. We're not including that point. So they approach 0 from both sides. So we have none on this one, no discontinuities. Okay, questions? So whenever I'm doing the limit here, one of those special limits that we learned whenever we did like squeeze theorem, it was in 1.8 where we looked at that. The limit as x approaches 0 of 1 minus cosine x over x always equals 0 for that. So whenever I'm doing this limit here, I could write like this step where I do the limit as x approaches 0 from the left of negative 1 times the limit as x approaches 0 from the left of 1 minus cosine x over x. So this whole expression right here, this whole thing right here would be 0. And then the limit of any limit of negative 1 is just going to give you negative 1 because it's just a constant there. And so that'll give you 0 for that. The conjugate possibly might work on that. It will be much more, it'll take a lot longer if you do it. If I had extra time, I'd chase that rabbit just to see, but we don't have time for that, so we'll keep going. All right, questions? All right, so you do sometimes run into like actual limits you have to solve whenever you're doing this. Most of them are going to be direct substitution, but not always. All right, and then here, I love these types of problems right here. And the AP exam likes these types of problems. ACT is not going to ask this problem because it's calculus material, but ACT loves to throw a bunch of letters in problems and make it very theoretical instead of just straightforward, right? So while it might not be this exact problem, they love this type of problem here. So we are supposed to find A and B that will make this continuous, right? And so what we have, A and B are just real constants, so these are just real numbers. And so right here, we got a quadratic. Quadratics are continuous everywhere. This is a line. Lines are continuous everywhere. And then we have a horizontal line, because that's just going to be like x equals a number, right, which is a horizontal line. Also continuous everywhere. So what we really need to know is about the places that these two right here would meet up. So like right here at -2, we need to know what's happening, right? So if I plug in, and I'm going to shortcut this, I'm not going to do limit notation because we got a lot of things to think about here. If I plug in -2, I'm plugging it in for the x. So if I do that in both of these equations, I should get something that's equal if this is going to be a continuous function, right? So that means a times -2 squared minus b should equal a times -2 plus 2. And so -2 squared is 4, so I got 4a minus b equals -2a plus 2. Can I solve that? I need to find a or b, but can I solve it with an a and a b both in the equation? I cannot. So I'm kind of stuck. So let's think about the other. Like, I could rearrange it some more, but I can't get rid of the b or the a in this case. So let's think about the other point at 2. So if I take 2 and I plug it in here for the x, and, oh, what about here? I got nowhere to plug in this 2. It just kind of floats off into the distance right there, right? Because you can't plug it in. But I would have a times 2 plus 2 is supposed to equal b. Or I could say 2a plus 2 equals b. Excellent idea, right? Because I can't solve that one by itself either, right? That has an a and a b. But if I already know what b is equal to, if I know that b is equal to 2a plus 2, then I could go over here and I could replace b with 2a plus 2. Okay, it's called substitution. Honestly, this technically is like a Math 1, like doing this, what you have just suggested here is Math 1. Would most Math 1 kids be able to still complete this 3 years later? Probably not. But it is substitution, so we got 4a minus, make sure you put parentheses around this, 2a plus 2 equals -2a plus 2. And so we'll distribute our negative here. 4a minus 2a minus 2 equals -2a plus 2. Let's combine our like terms here. We got 2a minus 2 equals -2a plus 2. I'm going to add this 2a to get it over here to this side. 4a minus 2 equals 2. We're almost there now. We're going to add this 2. 4a equals 4. So then I just divide a equals 1. And then, what do I have to do? Because I need the b also. Plug it in to either equation. The green one I have over here is easier, so I'm going to use that one. So 2 times 1 plus 2 is going to equal b, which is going to give me 4 for my b. So I get 4 for my b and 1 for my a.
So do we have to do the limit stuff now, or are we done after that?
I could have written this whole thing out with the limits instead, but because this is so much work, I wouldn't. And usually if you see something like this, it's going to be multiple choice. It is usually not going to require you to write out that limit notation, because technically what I'm doing here is I'm saying like my limit from my left equals my limit from my right, and I could use limit notation on this stuff, but it gets really long if you do that. So, I'm all right if you're not very precise. Now, tomorrow, I'm also okay on the homework if you're not very precise on your limit notation with those piecewise functions. But just know tomorrow we've got to be, okay? So your assignment, here is, 37 through 53 odd. It sounds like, wait, I didn't even put the page, did I? I think it's 96. Let me look and see. Yes. Now, it sounds terrible, but, like, the first one is 6 over x. That has a non-removable discontinuity at 0, right? So, like, these should be fast. You should be able to do them quickly, for these. So, it is page 96. Yes. They really mixed the desk up yesterday. I am not surprised. I was pretty sure Miss Burton was going to come down the hall yesterday. I had a big crowd yesterday. Miss Edwards' kids were here, on top of my regulars, so, and, yeah, picture's fine, yeah. And we got about 10 minutes, so go ahead and get started on that.